Okay, so in the UK it is 12 noon and it's time for session 3BC from Helmut from CompuWare, who is going to give you a presentation on, well, the title said VSAM's alive, and it certainly is. Please remember feedback at the end of the session. Very important for us for next year's GSE planning, and also I guess for Helmut too, to see how he came across. But you're all on mute, so if you have any questions, please put them in the chat. If possible, I will interrupt to ask those questions, or we will just keep them to the end. And with that, I'll hand over to Helmut.
Okay, Anna, thank you very much. I hope everybody can hear me. My name is Helmut Zwickelbauer. I'm working for CompuWare in Germany. And I have the opportunity today to tell you something about VSAM, in particular something about VSAM performance and how to speed up your VSAM jobs and VSAM applications. So I want to start with a few words about VSAM itself, what it is, and when it came to COS. And then I changed to ERM. This is actually the VSAM booster we are using. And I try to explain what makes a difference, how can we be better than VSAM, or how can we achieve some benefit compared to VSAM. And finally, of course, you have to know how you can enable ERM and what should you expect to see if ERM is used instead of VSAM for particular data set. Finally, I have a few features that VSAM doesn't have, and I want you to know how much VSAM you still is used in your shop, how much VSAM datasets are still active in your shop. Maybe you don't know. I think there is some VSAM everywhere. So let's start with VSAM. VSAM is pretty old, almost 50 years. It came in the 1970s. When IBM created this new access method. VSAM actually means virtual storage access method. This is a way to see a data set just like virtual storage. So you see a continuous area of data bytes, and you can access them by some byte address, some relative byte address relative to the beginning of the data set. This can be done with VSAM if you want. Of course, VSAM also supports accessing datasets by records, just like all other access methods did in the past. So just about the acronym VSAM. VSAM is not only used for the access method, so virtual storage access method, it's also used for the name of the dataset organization. So we talk about VSAM datasets to make it different from traditional sequential datasets. Okay, there are different types of VSAM datasets. The most important one is the key sequenced dataset. Key sequence dataset means we have some keys within the dataset, and you can access the data records by using a key. You provide a key in your application program, and VSAM finds the record that matches this key and presents it to your application. And you don't have to care how this works. It just provides a key and say get, and VSAM will return the record. So other dataset types, a simple one is ESDIS, entry sequence datasets. That is more or less a sequential method of processing data. So you read or write the records in order. and you write it sequentially and read it sequentially. We also have a method that's called relative record datasets. With this organization, you can access a record by its number. So if you know the number of the record you want to read, then you provide the number and you get VSAM returns the record. Very easy to use. And finally, there are linear datasets. And linear datasets is this type of VSAM storage that provides this virtual storage methods. So you can see a linear dataset just like you see virtual storage. This dataset is organized in pages of 4K, just the same way the virtual storage is used. And if you have an application that wants to make use of this, then you can do it. It's just like Data and Virtual is using it, for instance. So in the past, because VSAM is pretty old, in the past there was a lot of applications that used VSAM because it was easy to use. But over the years, many of those applications have been converted to DB2. But this required a major change of the application code. So you have to change your programs because DB2 uses a different style of data access. In a VSAM program, you always request one record and you update one record. In a DB2 program, you request a set of records by a select, and you can also update a set of records with a single command. So but not every shop changed to DB2, and of course, even for those shops who changed, not every application was converted. So we think there's still some VSAM left in almost every shop. And in addition, a lot of vendors still use VSAM for their own products. Let's see a small list. This is a list of vendor products that we know that are still used by customers these days. Maybe you have one of them. It's just a subset, of course. So for today's discussion, I want to focus on your application programs, your own written applications or your vendor applications that make use of VSAM datasets. I don't want to focus on DB2 because DB2 actually also uses VSAM. It uses VSAM linear datasets, but this has its own performance methods. There's nothing we can improve, not with our tool. And we also don't want to talk about catalogs or other system datasets that allocate VSAM to get space on disk and then do their own processing for let's say, for SMF recording of a checkpoints and for that stuff. So this is not my focus. I want to concentrate today on key sequence datasets because this is the most important one for VSAM, and this is the most heavy used in customer sites. Key sequence dataset means you can access the data records by providing a key value, and the dataset actually has two components. There's a data component and the index component. And this index component is used to find the record that you want to update or to read. And the key you can use, it depends on your application, of course. It can be any character string. It can be names or numbers or some references, timestamps if you like, or any combination of this. So it's up to you how long is the key. For VSAM, it's just a character string you provide in your program, in your application, and then VSAM will find the record for you. Actually, this works pretty well, but we think there is room for improvement, in particular if the data sets had become pretty large. And this is the point where IAM comes in. And now I have to explain a little bit what is IAM. IAM means Innovation Access Method. It was developed by Innovation Data Processing also in the 1970s. So it's almost the same age like VSAM. And it is, let's say, it's a high performance method for accessing indexed datasets. It's not a full replacement of VSAM. We don't see it like of a replacement, but you can replace individual datasets. Those datasets that don't perform pretty well with VSAM. Okay, what's the goal of ERM? I think we can actually say it in a single word. Focus of IAM is to reduce the number of IOs. This is an important thing. The number of IOs or execute channel programs, XCPs, should be reduced. And if you have less IOs, you also have less CPU time, and your batch job or your VSAM application is faster. This means you can use your CPU a little bit longer. You don't have to do upgrades of the CPUs. You can run your jobs with less service units, so it's less expensive. And finally, we have a way to reduce the size of your VSAM datasets. IAM datasets are smaller than VSAM. This also saves time in processing the dataset. So how can we do this? Well, in order to explain this, we have to have a look first. What is the issue with VSAM, in particular for large VSAM datasets? The KSTS dataset requires an index. And this index is nothing more than a list of all the keys that are used in your dataset. So there is a key sequence set, and if you have many records, then this key sequence set will become large. So the index, the VSAM index, is organized in multiple levels, and every level requires an extra IO. And this means in order to read a single record of your dataset, you have to do, let's say, 4, 5, or more IOs to the VSAM dataset, because one is a data IO and the others are index IOs. I explain it in a little slide. The VSAM index, it's seen here above the red bar. The VSAM index is organized in a so-called sequence set. The sequence set is a list of pointers where every key is listed, not exactly every key. It lists the last key of each block in the dataset. So you have a pointer to each block in the dataset, and you have a pointer that is refers to the high key in this block. And of course, if you have many records, the sequence set is pretty large, and you cannot afford to read a whole sequence set. So VSAM creates additional layers. There is an index set above the sequence set, and the index set is also a list of pointer where each pointer refers to a specific block in the sequence set. And this index set can have multiple levels, of course. This depends on the size of your data set and the number of blocks of your data set. So you always start with the top level index, and then we go down through all index levels, and finally you can come down to the data access. Actually, this is not bad. This is a method to locate a single record by, let's say, a few IOs, let's say 4 or 5 IOs. Not bad, but we can improve this now. We can improve this with ERM. And the IAM message is a little bit different. We don't split the data set into data and index part. We have it combined in one component on your disk. This component contains all data records in the prime area in the contains an index. And different to VSAM, when the dataset is opened, we load the full index into memory. Of course, this requires maybe a lot of memory, but we can use 64-bit address space for this, and then you have a lot of virtual storage. So if your index is loaded into memory, then you don't need any I/O on disk to locate a data record. You just, of course, you have to read the data record by a single I/O, but you don't use any I/Os for the index. And this makes processing much faster because you're doing one I/O instead of 5 I/Os. So this is just a very easy calculation. Okay. The loading of the index is done once during open, and then every access to any data record doesn't use any new index I/O. It just accesses the data directly. We use 64-bit memory for storing the index. Now that 64-bit storage is available. In the past, before it became available, we used CUS data spaces for this purpose because we didn't want to use the virtual storage of your application. Application memory was limited with 31-bit addressing, so it was limited to 2 GB. And for a large address space, some, let's say like KICS, like CICS, it would be critical if we used virtual storage for the index. Now with 64-bit memory, there's no more problem. We can use it in large areas. The second issue with VSAM is the split issue. I'm sure you already have heard about the VSAM splits, and you probably know what this is. Well, VSAM has its data blocks, and each block contains the records ordered by key. That's really good because this means we only need one index pointer to each block because we know within each block every records are ordered. But what does it mean if a new record comes in, if the record is inserted? You have to provide free space within each block to make room for the insertion. But finally, the free space is full, it's gone. And if you want to insert a new record in a full block, well, you have a problem. And this is the point where the split comes in. A CI split, actually a data block in VSAM is called a control interval or CI. So a CI split has to occur. And the CI split, it cuts the existing block into 2 pieces and has 0.5% of the data in piece 1 and 0.5% of the data is in piece 2. So half of the block is moved to a new control interval within, and that's within the same control area. A control area in VSAM is usually a full cylinder of data. So it's 15 tracks of data. It's a usual size for a control area used by VSAM. And in order to make this splits happen, there must be some free space in the control area as well. And if the control area is full, then you have to split the control area. And this means you have to split a full cylinder of data, and the half cylinder of data has to be moved to a different location in the file. And this is really a lot of I/O to do. This takes time. I think every VSAM user knows this split issue. If this happens within your KICS application, then you will see it because there is a short delay until the split is completed. What is ERM doing? Well, we try to keep it simple. When we insert new records, and there is no room in the prime data area, there is no room in the home block, let's say, where the record should be inserted, then we don't split anything, we just write it to the end of the dataset. We have an overflow area at the end of the dataset, and every record that doesn't fit in its home block will be written to the extended overflow, and that's all. We don't do any extra IOs, we don't move or reorder any data, nothing, just write a new record and it's finished. So we speed up the split issue extremely. The last major issue with VSAM, we already talked about it because you have to provide some free space. So it's the space issue. Every block in VSAM should have some empty space to be prepared for future inserts. And because of the split issue, you should also have to provide some empty blocks at the end of each cylinder in order to avoid those long CA splits. So because CA splits are really heavy in terms of IOs, in terms of processing time. So finally, you allocate a lot of free space within your VSAM dataset, but this, of course, this helps a little bit, but this doesn't help in all cases. Um, there are still cases when your blocks become full and your control area gets full and you have to do a split. And on the other hand, there are a lot of blocks where the free space is not used. So the space is still empty and the data set is much larger than it needs to be. So this is the issue with space because of the CI and the CA split issues. And this usually happens because the inserts that are done by your application are not evenly spread on all key values in your file. Most of the time, the index focus on a single area within your dataset, and this is the point where new splits are created. And the rest of the data set contains still empty blocks, empty CIs, and allocates more space than needed. And finally, one more thing about VSAM. VSAM is fixed to fixed block sizes of a multiple of 2 kilobytes. So you cannot use a half track block size. The half track block size would be something a little bit lower than 28K and 28 kilobyte. You can use 26 kilobyte with VSAM, but not 28, not this odd number of 27998. This is the half block size, the half track size. And this block size can be used by IRM. Actually, we can use half track or three blocks per track or 4 blocks per track. This is all these variations make use of the full track size in a 3390 device. The result of this, we can store the data in less space, in less tracks and less cylinders. And of course, this also means we can use less IO to process the same amount of data. So these are the major issues with VSAM and how they are addressed by IRM. So the question is, how can you enable IRM? And this is, of course, this is the interesting thing for you. Enabling IRM is really easy. If you have installed IRM, you have a load library, and all you need to do is to run the program IRM start. It's usually done during IPL. And once IRM start was running, it will load a set of modules into common storage. And the set of modules is called the VSAM interface. And once this VSAM interface is up, we will check every open to a VSAM dataset. And and every open we check, is this a real VSAM dataset, then nothing changes, or is this an IAM dataset, then VSAM is bypassed and all processing is done by IAM. So it's a test on the dataset level, it's a test during open time. What you have to change to make this work is just adding a small keyword to the define cluster. The define cluster is used to allocate the VSAM dataset, and you add the keyword owner $IAM. And if IAM VSAM interface is up and you run a define cluster with this owner keyword, then the dataset will become IAM format and no longer VSAM format. And this is all you have to do. There is nothing else to change. You don't have to change your JCL, and you don't have to change your application programs. Your application programs still think this is VSAM, and EIM behaves exactly like VSAM. So your application won't know about this change. It still thinks it works with a VSAM dataset, when in reality it's an IAM dataset. Also, changes are done by the access method when IAM is in use. So what if you have done this and you have some VSAM datasets converted to IAM, what should you expect to see? Well, I show you some samples that come from a test that was done at a customer site in Scandinavia, where the same job with the same data was running with VSAM, and a few minutes later we ran the same job with the same data in IAM format. And what you see here is a really big decrease of XCPs, of IOs. So the IOs come down, let's say in this sample, from 250,000 to come down to 60,000. So it's more than 75% less IOs. And this makes a difference for elapsed time. The job is running much faster. And it makes a difference in service units. So the job takes less resources, is less expensive. This is just one sample. I have other samples as well, because the result you see here, the benefit, it depends on the application, of course. It depends what your application is doing. This is something, let's say, something I expect to see in many VSAM jobs, but there are other things as well. The next sample, for instance, this one is some extreme result. It was really unexpected for me. The VSAM job was running more than 13 minutes. When we converted it to IAM, it was running 10 seconds. So how can it be? It was actually providing the same result, but in much less time. How can that be? It turned out that the application is opening the VSAM datasets for update, because it has to update a few datasets, when most of IO was in reality, it was sequential reading. So that means VSAM was tuned for update, for random readings, for random updates, but the application was doing sequential processing, and VSAM is not able to change its buffering for that case, but IAM is ready to do this, and IAM changed immediately to sequential processing, and it was reading one full cylinder of data in a single XCP, and this makes a difference in runtime system. A third example is something different. It is an application, it's doing a lot of tape IO. So VSAM is not the important part in this application, it's the tapes that is the important part. So we don't see a decrease of XCPs numbers, small decrease of XCPs numbers, and we don't see a decrease of service units, because it's almost every service unit is spanned with a tape IO. But we see a decrease of elapsed time, because we can change the VSAM processing and make it faster. And this, let's say that the job is the same in terms of service units, but it's faster. It went down from more than 7 minutes to 4 minutes in this sample. So it really depends what your application is doing. I cannot predict how fast it will be if you convert it to ERM, but there is some potential. That's important to know. Well, up to now, I discussed the major issues or features of ERM. We have index in virtual storage. We can avoid all the split issues, and we can make the dataset much smaller. And all those effects bring you to less XCPs. So this makes things much faster. But there's more to know. With 64-bit memories is available on modern CPU hardware, you can have a lot of data buffers in storage. This is something really new because you can do this not only in batch jobs, you can do this in your CICS environment as well. We have many files are open in the same time, and you can assign a lot of buffers. You can assign, these buffers are assigned in 64-bit memory, even for those applications that are not enabled for 64-bit. So if your application is still running 31-bit, that's a usual thing at the moment, or if you have some old application that is running in 24-bit mode, no problem. The ERM buffers are allocated in 64-bit memory, but the application will see a copy of the buffer in its own addressing mode. So it's enabled for use for every kind of application. The number of buffers that are allocated for each dataset is dynamically adjusted. You just provide a minimum number of buffers and a maximum number of buffers, and ERM tries to optimize the number of buffers as the application continues to work. This is called real-time tuning. Real-time tuning is some type of dynamic buffer management. We use a method called least recently used, LRU buffering. So the buffer that was not used for a long time is the first buffer who will be reused by new data. Something similar to paging in COS. If it turns out that the sequential is doing sequential IOs, then ERM will immediately switch to sequential read ahead. This means we're reading more data than is requested by the application. The application usually requests to read the next block, and we read a full cylinder of data in one IO. So we do a lot of read ahead, and we can save a lot of IOs if sequential processing times comes in. And we can defer writes to the data set. That means we write not every block in one IO, so we can also write multiple blocks in a single IO. You can turn this on even for kicks if you want. So the major benefit here of real-time tuning is that we can switch between random processing and sequential processing within half a second, let's say, or even a smaller period of time, because ERM just sees what your application is doing and adjusts his buffer strategy based on the actual IO demands. One more feature is data compression. We have an built-in software compression tool that reduces the size of each record and the size of each block. And this means the data set will become smaller. And this also means we have to do less IOs, less XCPs for reading the same amount of data. This speeds up the whole thing and it makes it less expensive. You save CPU cycles. But of course, if your target is to save CPU cycles, then you have to keep in mind that compression, of course, will also consume some CPU cycles. So if your target is to minimize CPU usage, then you better turn data compression off. It's enabled by default, but you can turn it off as you like it. And you can change it if you want from software compression to using system Z hardware compression. System Z hardware compression requires a data dictionary, a compression dictionary, and we usually build this dictionary during loading of the file. But if you want, you can provide your own customized dictionaries, and then you may achieve higher compression rates. So if your focus is higher compression, then you may use System C hardware compression. If your focus is saving CPU cycles, then you turn it off. And by default, we are using software compression. That is a balance between reducing the size of the data set and optimizing the speed of processing. One more interesting feature is a OneTime report. A report is available upon the close of each dataset. When the dataset is closed, we can provide this information about the dataset itself. How was it defined? How big is it? What is the record length and the key size and those things? You also see when it was defined, and the loaded date is the time when it was reorganized the last time. A reorg will reload all the data, so you can see when was the last reorg in the loaded date, and the update date is usually the time the dataset is closed because it was updated by your application. You also see the number of records, the number of records deleted, inserted. This is available for VSAM too, but it's here it's part of the OneTime report because of course you have to know what's happened with it. But more than this, we have a detailed list of actions that happen to your data set. So the green values here, you can see what your application was doing. Was it processing sequential or it was random? Did it issue any updates or inserts or not? You can really see what your application was doing to these data sets. And you can see in the blue area here, what did this mean to the physical I/O? How much blocks did we need to read from disk? How much buffers did we use? How much memory did we use in your address space? How much big was the index and the 64-bit area and this stuff? So it tells you a lot of details and how many buffers were used, for instance, and tells you a lot of details of what's really happening with your dataset. Okay. This OneTime report is available at the close time of the dataset, and it will be written to sysprint or to sysout if you provide some ERM info DD statement. It's usually a sysout dataset. Then you can see it directly within your job output, or if we can write it to SMF if SMF recording is enabled. So just like VSAM writes the record type 64, IAM writes a different record type. You can select the number, and then you can do this reporting later by checking SMF records. One more interesting feature that we write recommendations on tuning. So if it turns out that IRM real-time tuning detects that the number of buffers should be increased, then we tell you. There's a message, let's say, specifying a buffer number value greater than you have now may improve performance. And at the same time, we tell you if the data set should be reorganized. If the overflow area becomes too large, then there is a point in time when we have to do reorgs, just like VSAM. VSAM datasets have to be reorganized as well. And we think IAM, of course, IAM have to be reorganized, but we think less often compared to VSAM. Okay, what's more? We have some advanced functions that are not available for VSAM. And the most interesting from my point of view is the dynamic reorganization for kicks. So if your data set is open in kicks, and this means it's open all the day and probably all the week, and you have to reorganize it from time to time. Reorganizing means, of course, you have to make a copy of your data set. Reorganizing means the traditional reorganize is done by IDCAM's repro. You write it to a sequential data set on tape, and then you read it in again and replace the existing VSAM data set. This means during reorg, no application can use your file. The application is not available to a file. And this is the thing IAM dynamic reorg is trying to address. What we are doing, we're doing the reorganizing on a copy of the file. So we copy it first, and then we reorg the copy. And while we do this reorganizing, as I say, it will run a minute or two, your kicks application will still work with the original data set and will do updates and inserts and deletes to this original data sets, and we take care of this. So we detect these changes to your original file and apply these changes at the same time to the reorganized copy. And finally, all we have to do is exchange the data sets. So we have to close the original data set and rename it. And then we reopen our reorganized copy and we bring it up on the original dataset name and open it to kicks. And this will just take a few seconds. And if your application is doing some IO to this dataset at that time, then we have an exec provided that enables your application to tolerate this. That means your application is just waiting 1 or 2 seconds and then processing continues. And it continues on a new reorganized copy of the dataset. We had done some benchmark on this with using 3 datasets. The big one was had 50,000 tracks. The next one was only 25,000 tracks. And the third one, it was 70,000 tracks. So we did a reorg for all three datasets. In IDCAMs, it's sequential. Every dataset is reorged after the other. And with ERM, we can do it sequential or in parallel. Let's see the result, just a moment. Here. On the blue bar is the processing time used by VSAM IDCAMs. So it's writing the dataset to sequential tape, reading it in again and replacing the original file, then do the next dataset and do the third dataset. All this together takes about almost 15 minutes. When we do this with IAM, the regular reorg for all three datasets will take something more than a single minute, 1 minute and 70 seconds. But if you do the dynamic reorg in kicks, then the time that kicks has to wait for the dataset is only 2 seconds. And this is the time your application, your kicks transaction has to wait if it tries to access the dataset at that time and actually the rename stuff is running. So this is a very small not an interruption, a delay in your kick system just for those transactions that work with those 3 datasets, and everything else is continued to work. And your application probably won't notice there was a small delay, and you have reorged your dataset. That's a real improvement, I think. One thing I should mention is record level sharing. Record level sharing, of course, exists with VSAM as well. I think it also exists with VSAM longer than it exists in ERM. Record level data sharing means you can share the same data set by multiple address spaces. So usually it's shared within KICS and within some batch shop. For IAM, because we have the index in memory, we don't detect if somebody is changing that index or is changing the data set at all. So in order to accept those changes, IAM record level sharing requires an additional address space that has to run on the LPAR. And this address space will actually handle all IOs. So the application that try to update or read the file will in reality pass this request to the IAM address space, and the IAM address space will do the IO and return the data by some cross-memory service. This is really different to VSAM, and it's available on a single LPAR. So we have a few more limitations, things you cannot do with IAM. Fortunately, these are functions that are seldom used in VSAM. For instance, if you want to process a data set by block by control interval, or if you want to access it by a relative byte address. This doesn't work with IAM key SDS files. So if you have such an application, you cannot convert it to IAM. The same thing applies to enqueue sequence datasets. We cannot update on block level, no update by control interval. We just can update individual records. And with RRDS, it's the same. We cannot update by control interval except if one record is one control interval, because we can update individual records, but not control intervals. One important issue to know, record level sharing is at the moment just available on a single LPAR. It's not available on Sysplex. This is in development, and I hope we will have this feature ready in, let's say, in 1 year, maybe 2. And then we can share the dataset on multiple LPARs as well, just like VSAM is doing it at the moment. So if you have such applications, you also cannot convert it to IAM at the moment. So do you have some VSAM datasets in your shop that are still used, and how much are they used? We have a little report that you can run on your site that just reads SMF records. It's a type 6, it's a type 30 and a type 64. The type 30 is job activity and type 64 is VSAM statistics. And then with this little web report, we can check how many VSAM datasets you still have in use and how are they used, how many IOs occur in what dataset. So we can identify the top level candidates to be converted to IAM. And we can show you how many splits you have in some datasets or how many inserts. So we also can identify the candidates that would be a candidate for dynamic reorg, for instance. So you can run this reporting tool on your shop, or you can send us your SMF records and we can run this for you, and we can check if you have a potential for IAM or not. So that's almost everything I wanted to say in this time. Just keep in mind that IAM can have really significant benefits to selected datasets, not to every dataset, but to selected datasets. It is very easy to use, very easy to implement. You don't have to change anything. In particular, you don't have to change any application program. You don't change your JCL. You just convert it by the defined cluster. You copy the dataset to a new cluster and add a simple keyword $IAM, and the new cluster will be IAM format. And your application doesn't know, and it doesn't need to know. Everything looks like VSAM. The only difference is seen by your backup tool. Your backup tool will see a sequential non-VSAM dataset instead of a VSAM dataset, but it can backup it, of course, so no problem. Okay, thank you very much for your time. If you have some questions, then please use your chat function, so I can respond. Otherwise, I would like to make you aware that CompuWare hadn't became part of BMC now, and there is a mainframe service, a survey provided by BMC, and you can download the result if you want. Please don't forget to submit some feedback. There is a link provided here in the document. You can download the slides in a PDF and use this link to provide the feedback if you want. We would appreciate it. Finally, don't forget there is a charity event at the GSE conference because everything is virtual and there are some people involved. They had a lot of work to do. So it's also is about money, of course. So thank you very much. If there are no questions in the chat, then I hope yes, I have almost 10 minutes left. So if somebody has a question, just let me know.
Okay, so I have set the preferences so that you can unmute yourself if you have a question for Helmut. And as he mentioned, yes, the charity this year by the GSE, we have one or two every year, and we normally manage to raise quite a considerable sum. So if you can donate, that would be brilliant. You haven't had to pay anything to come to the GSE this year, so that's a good reason. And you would have been buying a raffle ticket at the gala dinner, so there's another saving that you've made that perhaps you could hand over to charity. Okay, so if you have any questions, please feel free to ask them now.
Thank you very much for listening and have a good time. Enjoy your lunch and perhaps we'll see you again another time. Bye.